Welcome to New Findings of the Universe. Today we are talking about a problem that sounds small, like a number on a page, but it may change our entire story of the cosmos. For decades, we have repeated an idea with confidence. The universe is expanding, and that expansion has a rate we can measure. That rate is called the Hubble constant, and we use it to calculate the age of the universe, its size, and even how galaxies formed and evolved. But here is the unsettling part. When we measure the expansion using one method, we get one number, and when we measure it using another method that is just as serious, we get a different number, and the difference is not minor. The gap is not shrinking. It is getting reinforced by better data. And in science, when two trustworthy paths lead to two different destinations, that is not a footnote. That is an alarm. To feel why this is so intense, we have to rewind to where the idea began. For most of human history, the universe seems small and orderly. Earth below, sky above, lights moving in patterns that felt eternal. Then came models that placed Earth at the center. And later, a radical shift that removed us from the throne, the Sun at the center, and Earth as just one of several planets. Centuries passed, and we still believed our galaxy might be all there is. Until one night, staring at a faint smudge in the sky, someone proved that smudge was not a cloud inside the Milky Way. It was another entire galaxy filled with its own stars. At a distance so large it shattered the imagination of the time. And just like that, the universe stopped being a place and became an ocean. Millions of galaxies separated by unimaginable stretches of space. But the true shock came when distance met motion. These galaxies were not only far, but they were getting farther. Their light arrived, stretched, shifted toward red, as if space itself was pulling the waves longer while they traveled. And if space can stretch light, then space is not a fixed stage. It is something that changes. That was the revelation. The universe is expanding. Up to that point, the story was beautiful. The problem is that now, when we try to measure exactly how fast it expands, the numbers do not agree. And if the expansion does not agree, then the past we calculate and the future we predict may be built on shaky ground. Stay with me, because what comes next is the Hubble tension, and it may be turning into a cosmic crisis. And before we go deeper, if you love these stories where the universe becomes a real mystery, subscribe to the channel and join me on this journey. To understand the Hubble tension, imagine the universe is a movie and we are trying to figure out the speed at which it is playing. One way is to look at the present. Measure how galaxies move today. Measure their distances, measure their redshifts, and calculate the number. That is the late universe approach, the expansion as we see it now, billions of years after the Big Bang. The other way is to go back to the beginning. Look at the oldest frame we can possibly see, and from that calculate how the universe must have grown to become what we see today. That is the early universe approach, based on the cosmic microwave background. The ancient light that is like a thermal echo from a baby universe. Both approaches sound reasonable. Both are backed by powerful instruments and decades of work. And yet, when you do the math, one gives a faster expansion rate and the other gives a slower one. In numbers, the late universe method tends to land near 73 kilometers per second per megaparsec, while the early universe method lands near 67. To most people, that might sound like a small difference. But in cosmology, it is huge. It can change the inferred age of the universe and the way structures form over time. Think about what the late universe method really requires. You need reliable distance markers because there is no cosmic tape measure. So, astronomers build a distance ladder, a chain of measurements. First, you calibrate nearby distances. Then you step outward using special kinds of stars that pulse in a predictable way. Then you go farther using stellar explosions bright enough to be seen across the cosmos. If each rung is calibrated correctly, the final number should be strong. Now think about the early universe method. Here, you are not measuring galaxies moving away today. You are reading a frozen pattern across the sky. Tiny temperature differences in a radiation field that comes from a time when the universe was only hundreds of thousands of years old. That pattern is not random. It encodes the distribution of matter and energy back then. With the standard cosmological model, that pattern can be evolved forward to predict what the expansion rate should be today. The critical point is that these two approaches should converge. If the model is correct and the measurements are correct, better data should bring the numbers closer. But the opposite is happening. The difference is becoming more solid. And that is what turns a curiosity into a crisis. Because we are not talking about one old telescope or one flawed dataset. We are talking about multiple precise measurements that keep pointing to the same disagreement. And if you are wondering what could be wrong, the answer is unsettling. It could be something missing in our understanding of the universe. Or it could mean the model we trust is incomplete. Now we reach the heart of why this tension matters so much. In physics, some numbers are like pillars holding up a building. Change a decoration and nothing happens. Change a pillar and the structure shakes. The Hubble constant is one of those pillars. It connects to the age of the universe, the density of matter, the growth of galaxies, the evolution of clusters, and the role of dark energy, the mysterious ingredient we use to explain why the expansion is not slowing down but accelerating. For a long time, the standard model, often called lambda cold dark matter, has been a remarkably successful machine. Ordinary matter, dark matter, a cosmological constant representing dark energy, and Einstein's general relativity as the mathematical language. This model does not just explain the cosmic microwave background. It also explains the large-scale distribution of galaxies, gravitational lensing, and many other observations. That is why it is treated with respect. But for that same reason, if the Hubble constant does not fit, the problem is not local. It is a sign that something deeper may be missing. Imagine building an enormous puzzle. Almost every piece fits, and the picture looks clear. But in the center, there is a hole that refuses every piece you try. You can force one in, but then the rest of the puzzle bends. The Hubble tension feels like that. If you accept the lower value from the early universe, the story fits a universe about 13.8 billion years old, with a future of ongoing expansion driven by steady dark energy. But if you accept the higher value from the late universe, the universe may be younger. And we have to adjust what we think we know about the early universe, dark energy, or even gravity itself. And this is important. Scientists do not want to break the model for entertainment. Science is not a sport of destroying theories. It is a process of explaining reality more accurately. If the model is incomplete, it gets refined. If there is a systematic error, it gets found. But when the mismatch persists, despite increasing precision, researchers begin to seriously consider new physics. Many possibilities are on the table. Maybe dark energy is not truly constant. Maybe it changes over time. Maybe there was an extra burst of energy in the early universe that altered the expansion history. Maybe dark matter is more complex than we assume and can decay or interact. Or maybe, and this is the most dramatic option, we need a modification to how gravity behaves on cosmic scales, something that would force us to rethink parts of relativity. Each of these ideas is massive. They are not small tweaks. They are blueprint changes. That is why the Hubble tension is not just an argument about measurements. It is a question of whether we really understand the script of the universe or whether we have been reading an incomplete version. Let's talk about why the late universe measurements feel so convincing and why they could still hide traps. To measure the expansion today, you need two things: how far galaxies are and how fast they are moving away. The speed comes from redshift, the shifting of spectral lines toward longer wavelengths when an object is receding. That part is fairly direct. The distance is the hard part. So we rely on distance indicators. Historically, one of the key tools was Cepheid variable stars, stars that pulse with a rhythm that reveals their true brightness. If you know the true brightness and compare it to how bright they appear, you get distance. Then to go much farther, astronomers use type Ia supernova. Stellar explosions so bright they can be seen across vast distances and with properties that allow them to be standardized. This is how the cosmic distance ladder is built. With modern telescopes, that ladder has been refined enormously. And the Hubble constant coming from it stays high. And it is not only one approach. Independent methods also push high. Some galaxies host powerful microwave amplification near central black holes, creating a maser like a laser, but in microwaves. These signals can be mapped with geometric precision, allowing distance measurements that do not rely on the same ladder in the same way. When astronomers use this method, they also get a high expansion rate. There are also studies that focus on supernova in specific clusters and combine them with large-scale surveys designed to map cosmic structure. Again, the number does not drift down toward the low value. It stays high, sometimes even higher. And when different late universe roots agree with each other, it becomes hard to dismiss them as simple error. But science remembers something important. Systematic errors can hide for years. Dust can dim light. Stellar populations can shift calibrations. Supernova may not be as uniform across environments as we assume. These possibilities are studied intensely, as the community wants to be certain before concluding the universe is demanding new physics. Now return to the early universe side. The cosmic microwave background does not hand you the Hubble constant directly. It gives it to you through a model. It is like looking at footprints and reconstructing the animal. If the model has even one slightly wrong assumption, the inferred number can shift. So the low value might be saying the standard model fits the ancient sky beautifully. But perhaps the early universe had an extra ingredient that the model does not include. That is why this tension cannot be resolved by simply saying one side is wrong. Both sides have strong reasons. When both sides have strong reasons, the question becomes deeper. What are we missing? What property of the universe is hiding behind this disagreement? Now we enter the zone where the hypotheses start to sound like science fiction, but they come from serious mathematics. If the early universe and late universe disagree, one possible solution is that something changed along the way. Something we are not accounting for. That is where ideas like evolving dark energy or extra early energy come in. Think about dark energy first. We treat it like a constant, something that lives in space and pushes expansion uniformly. But what if it is not constant? What if its strength changes over time? If dark energy behaves differently in the early universe, then the cosmic microwave background would be interpreted differently, and the predicted Hubble constant today could increase. Moving closer to the late universe value. The problem is that any change must also match many other observations. You cannot fix one number by breaking 10 other things. Another idea is early dark energy, a temporary component that existed for a short time after the Big Bang, influencing expansion early on and then fading away. That could alter key scales encoded in the cosmic microwave background and raise the inferred value today. It is elegant because it targets the bridge between the early snapshot and the present. But the cosmic microwave background data are extremely precise, so the window for this fix is narrow. There is also the possibility of decaying dark matter. If some fraction of dark matter changes over time, the evolution of structure changes. The gravitational landscape changes, and the expansion history shifts. These scenarios are tested with huge simulations. And then there is the bold option: modify general relativity on the largest scales. Einstein's theory passes every local test with stunning accuracy, but the universe is a laboratory of unimaginable size. If gravity behaves even slightly differently across cosmic distances, it could affect expansion and resolve the tension. It is risky because it opens a massive theoretical door, but it is still a scientific possibility. Yet, among these complex ideas, a newer proposal has gained attention because it feels oddly simple. What if the universe has an extremely slow global rotation? Not a visible spin like a top, but a subtle cosmic twist so slow it would take hundreds of billions of years to complete a turn. Slow enough to evade detection in obvious ways, but real enough to influence expansion over long time scales. The appeal is that this does not necessarily require breaking known laws. Add a tiny rotation term into the model, and the early universe can align with a lower expansion rate, while the present universe aligns with a higher one. In other words, it could allow both numbers to be valid in a single extended framework. Of course, this is preliminary. It is not confirmed. It is a clue that must survive many tests against the cosmic microwave background, galaxy surveys, lensing, and every other cosmic measurement we have. But it is the kind of idea that reminds us how much we still do not know. Even now, with sky maps and space telescopes, we may have overlooked something as basic as whether the universe itself has a faint, slow spin. Now picture what a rotating universe would really mean. We already live in a cosmos where rotation is everywhere. Earth spins. The solar system orbits the galaxy. The galaxy rotates. Galaxy groups and clusters have complex motions, so it is not crazy to ask whether the universe could have some global rotation or primordial vorticity. The real question is whether such a rotation could exist without contradicting how uniform the universe looks in every direction. Here is what makes it interesting. The universe is extremely uniform on large scales, but not perfectly. There are small anisotropies, tiny differences, and we usually interpret them as primordial fluctuations amplified by gravity. A very slow rotation might hide inside those subtleties, not shouting its presence, but leaving faint statistical fingerprints. It would be like a lake that looks still until you watch floating leaves for hours and notice a gentle current. Researchers explore this with cosmological solutions in general relativity. They introduce rotation parameters and examine how expansion evolves. Some preliminary calculations suggest that the accumulated effect over billions of years could shift how we connect the early universe inference to the late universe measurement. That is exactly what we need, a mechanism that does not destroy the standard model but extends it. But beauty is not enough. An idea wins only by surviving tests. If the universe rotates, it should leave observable traces. Maybe in the polarization patterns of the cosmic microwave background. Maybe in subtle alignments of large-scale structure. Maybe in statistical patterns we currently dismiss as noise. If those traces do not appear, the idea collapses. What makes this moment exciting is that we are entering an era where these tests will become far stronger. We have missions and instruments that measure the cosmic microwave background with extreme precision, and surveys that map millions of galaxies in 3 dimensions. Every year brings new data that can confirm or kill hypotheses with increasing clarity. That means the Hubble tension is not going to remain a dinner table argument forever. It is moving toward a resolution. And we cannot forget the simplest possibility. The problem might still be a hidden systematic error, a calibration bias, an overlooked astrophysical effect in stars, a modeling assumption in the early universe reconstruction. Sometimes revolutions come from new particles. Sometimes they come from finding a 1% error that no one noticed. The Hubble tension sits right at that uncomfortable boundary. But even if it turns out to be a systematic error, the hunt will be worth it. Because to find it, we will have to understand stars, dust, supernova physics, galaxy environments, and cosmic evolution at a deeper level. And if it is not an error, then we are staring at something bigger, a missing piece of reality. That is why the expansion of the universe is no longer a settled textbook line. It is becoming a live question again. And when a live question connects to everything else, the universe feels once more like a mystery in motion. Let's do a thought experiment. Imagine you have 2 perfect clocks, both built with the best technology possible. You place them side by side, and they disagree. You cannot dismiss one as a toy because both are laboratory grade. So you have two options. Either one has a hidden flaw, or time itself is behaving differently under conditions you do not yet understand. The Hubble tension is like that. The early universe method reads the clock of the cosmic microwave background, the oldest light we can observe. Combined with the standard model, it gives a lower value. The late universe method reads the clock of galaxies, variable stars, supernova, and geometric distance indicators. And it gives a higher value. And the unsettling part is that as late universe measurements become more precise, they do not drift down toward the early universe value. And as early universe data becomes sharper, they do not drift up toward the late universe value. So the universe is telling us something. It may be saying the model is incomplete, or it may be saying the measurement contains a persistent bias. And that second possibility sounds boring, but it is brutally difficult. Because it would mean the bias is hiding inside a complex web of methods that many experts have tested for years. That is why researchers keep building alternative measurement routes, methods that do not rely on the same assumptions. Each new method is like adding another judge to a cosmic trial. And so far, several of those judges have supported the higher value. That is why some scientists are starting to describe this not as a tension, but as a crisis. But something good is happening too. This tension is forcing cosmology to become more careful and more humble. It is forcing old assumptions back onto the table. It is pushing better instruments, deeper sky surveys, stronger simulations, and bolder theory work. It is as if the universe is training us. Now think about what the future looks like. If the final answer is the lower value, the standard model remains strong. But we must understand why the late universe measurements were biased upward. If the final answer is the higher value, then the universe is younger than we thought, and the early universe story needs adjustment, possibly involving new physics. And if it turns out that both values can be correct in a deeper framework, then we need a theory that naturally produces both. Perhaps through something like a slow cosmic rotation or another subtle effect that changes expansion in a non-trivial way. Any of those outcomes is exciting because none of them is trivial. We are talking about the script of the universe, how it began, how it grew, and what is coming next. And once you see that, you cannot look at the night sky the same way again. Because every point of light becomes part of a massive investigation. Let me close with something that matters. Science is not a collection of final answers. 'Tis a machine designed to correct itself. And when that machine finds a contradiction, it is not a failure. It is an opening. The universe has no obligation to be simple. We are the ones who want it to fit into a clean model. And sometimes it does, for decades, until a new measurement forces us to look again. The Hubble tension is that look again. It is a reminder that even ideas that feel solid, like cosmic expansion, can still hide deep questions. And what makes it thrilling is that this is not philosophy. It is data. It is telescopes and sky maps and ancient radiation and stars that pulse like beacons and explosions that light up distant galaxies. All of it is real. All of it is measurable. And yet, the numbers are telling two different stories. If the solution is new physics, we may be on the edge of a cosmological revolution, something that reshapes our understanding of dark energy, dark matter, or gravity. If the solution is a hidden systematic error, we are still going to learn how to measure the universe with even greater precision. And if the solution includes something like an incredibly slow rotation of the universe, then our picture of the cosmos becomes richer. A universe that not only expands, but may also carry a faint global twist revealed only through patient observation. What does seem clear is that we will not sit with this mystery forever. In the coming years, with new surveys and new techniques, the gap will be explained one way or another. And when it is, we will rewrite part of the universe's story, maybe just a chapter, maybe the structure of the book, And that is where you come in. This channel exists to follow these mysteries while they are alive, while the evidence is still arriving, while ideas are still being tested. This is not a museum. This is discovery in real time. If you enjoyed this journey, subscribe to New Findings of the Universe. Turn on notifications so you do not miss the next episodes. Because this cosmic crisis is not the end. It is the beginning of a new stage in our understanding. Share this video with someone who loves astronomy, and tell me in the comments what you think the solution will be. A hidden error, new physics, or a universe that slowly spins. I am Chin, and I will see you in the next finding of the universe.